All right. Perfect. So, hi everyone, and welcome to this TMB meeting for the first of this week. We have today with us Mark Griffiths from Denmark. He's an aspiring PhD student, and he will be presenting on Inferential Learning-Amortized synthetic gradient networks, a scalable framework for causal learning and efficient training in neural networks. So, Mark, you have about 40 minutes for a presentation, give or take 10 minutes. And then there will be a Q&A from the audience, and then there will be a 30 minutes roughly of summary and feedback by Carl. Okay, so Mark, you have the floor.
Perfect, thank you. So good afternoon, everyone. Thank you for being here. My name is Mark Griffiths, and I'd like to present my PhD proposal. So this is what the topic of the presentation is on, and I'm excited to introduce my proposal for a novel neurocomputational architecture that I hope will streamline the training of neural networks. This architecture should reduce computational costs and optimize training so that successful and efficient convergence on the global minima is more likely. I have called this framework the Inferential Learning-Amortized Synthetic Gradient Network, or IL-ASGN, and it is designed to revolutionize how we approach causal inference and efficient training in artificial neural networks. As the subtitle suggests, IL-ASGN is designed to be a scalable framework that combines causal learning with efficient training methodologies. The main motivation behind IL-ASGN lies in addressing challenges such as the high computational cost of backpropagation, parameter interference during training, and the lack of explicit causal reasoning in many existing cutting-edge models. IL-ASGN borrows from neuroscience to give rise to machine learning performance and lends itself to economical translational applications on neuromorphic hardware. In today's talk, I will explain the key motivations, technical innovations, and applications of the IL-ASGN framework. Artificial neural networks are virtually always trained using the backpropagation of error algorithm. Despite being the backbone of most ANNs, backpropagation is computationally expensive. Additionally, the sequential nature of backpropagation means that as we update one part of the network during training, it can inadvertently affect other parts, leading to inefficiencies and slower convergence. This is known as parameter interference. Finally, backpropagated models lack the ability to integrate causal inference. IL-ASGN addresses these three major challenges by combining local learning, synthetic gradients, and variational Bayesian techniques such as uncertainty calculation and causal modeling. This makes IL-ASGN a paradigm-shifting approach to neural network design. It allows for parallelizable, efficient training by replacing traditional backpropagation with synthetic gradients, reducing both computational expense and parameter interference. Additionally, IL-ASGN has the capacity to integrate causal modeling directly into the learning process, enabling the network to go beyond correlation and identify meaningful causal pathways. The modular nature of IL-ASGN makes it an accessible and cost-effective solution for training user-supplied backpropagation networks. IL-ASGN focuses on four key objectives: reducing interference between weights, optimizing computations through amortization, enhancing causal understanding by isolating critical pathways, and scaling seamlessly to handle large complex models. Let's take a look at each of these. First, IL-ASGN aims to reduce interference between parameters. By using localized updates through inferential learning, it ensures that parameter updates don't conflict with one another, allowing for more efficient and stable training. Second, it focuses on optimizing computation through amortization. This means reusing synthetic gradients across iterations to avoid redundant calculations, significantly improving computational efficiency. Third, IL-ASGN enhances causal understanding by isolating meaningful pathways through amortized synthetic structure learning. The network efficiently identifies the key causal relationships that matter most, improving both interpretability and decision-making capabilities. Finally, the framework is designed for scalability. Parallel updates allow for faster training, making it possible to handle large, complex models and high-dimensional data sets seamlessly. Together, these objectives ensure that IL-ASGN is not just efficient and scalable, but also is capable of understanding and leveraging causality in ways that traditional networks cannot. In the next slides, I'll show how these goals are achieved through the framework's architecture and theoretical foundations. IL-ASGN's architecture combines principles of inferential learning, synthetic gradients, amortization, and variational Bayes to tackle complex, high-dimensional data efficiently and causally. The architecture relies on two coupled components: the guide, which focuses on high-level inference and causal reasoning, and the executor, which handles real-time learning and adaptation. Inferential learning is a biologically plausible alternative to backpropagation that uses local errors in the guide computational graph in conjunction with the Gaussian forward model and variational Bayesian free energy minimization. It is therefore not sequence locked in the way that backpropagation is, and can be modularly updated using parallel processing. Synthetic gradients are computed locally and asynchronously by the IL-ASGN guide and are passed to the chained executor network. Sorry. So here's inferential learning. I've just got a slide on that I flipped through, and you can see you've got the local errors. And what you can do here is iteratively in parallel, in a parallelized fashion, you can update the forward sweep before the backward sweep arrives. So this at the top shows the backpropagated computational graph chain, and at the bottom it shows the inferential learning or predictive coding chain. And that's the key advantage here, that you can have localized learning that isn't contingent on waiting for a backward sweep. So back to synthetic gradients. Synthetic gradients are computed locally and asynchronously by the IL-ASGN guide and are passed to the chained executor network, where they are adjusted in weight against the true gradients produced by this network using the TD lambda mechanism from reinforcement learning. These gradients are amortized in that they're stored and reused across iterations, reducing redundant calculations and increasing computational efficiency. And here again is, this is from a paper on synthetic gradients, and we've got network B predicting, based on its model of network A, predicting synthetic gradients for network A, and network A responding with the in time with the true gradients, and then that's used to form a cost function for network B. So network B gets better at predicting synthetic gradients for network A, and network A gets better at doing what it's supposed to be, whatever it's supposed to be doing. So it's like an adversarial, generative adversarial network, and that's something I sort of use in IL-ASGN. So variational Bayes nature of this framework allows for the calculation of uncertainty as well as causal modeling of significant pathways in the guide. Amortization of this modeling is apparent in that structure learning calculations are reused in pathway isolation. Causal modeling enhances the precision with which the synthetic gradients steer network evolution in both the executor and reciprocally in the guide. So now that we've outlined the objectives of IL-ASGN, let's dive into its theoretical underpinnings. At the core of this framework is inferential learning. This concept focuses on the local error minimization and gradient estimation, thereby reducing reliance on backpropagation and increasing resilience to problems like vanishing exploding gradients. Inspired by biological error computation, it enhances the network scalability and stability by minimizing parameter interference during training. Next, we incorporate synthetic gradients, which are used to approximate local gradients without requiring full backpropagation. These gradients enable asynchronous local updates, making the training process more efficient and parallelizable. By blending true and synthetic gradients, we can balance short and long-term dependency learning. This combination allows IL-ASGN to retain both computational efficiency and learning accuracy. Amortization, due to gradient storage and reuse, further enhances the efficiency of gradient computation. To recap further, another essential component is structure learning. By pruning non-essential connections, the network isolates meaningful causal pathways. This process doesn't just improve computational efficiency, it also enhances interpretability by focusing learning on the most relevant relationships. Structure learning is amortized by the storage and reuse of pathways in its isolation process. Finally, TD lambda, a reinforcement learning inspired mechanism, plays a critical role in blending synthetic and true gradients. This ensures the framework captures both immediate and delayed feedback, aligning with dynamic and nonlinear systems. Together, these theoretical components form the backbone of IL-ASGN, enabling it to tackle complex problems while remaining efficient and interpretable. In the next slide, we'll see how these elements come to life in the architecture through the guide and executor components. I'd like to define the IL-ASGN network as a guide and the chain network that trains in parallel with the guide as an executor. The guide and executor form a complementary pair, resembling the generative model and agent in active inference. Together, they can emulate a biologically inspired system which is capable of advanced decision-making and adaptability. The guide serves as a high-level generative model which predicts causal relationships and simulates contextual environments. It generates synthetic gradients to guide the executor's learning process. The executor operates as a real-time actor, processing live data and adapting its responses dynamically. Thus, the guide addresses the challenge of causal inference by simulating high-level context and generating synthetic gradients. The executor complements this by mitigating parameter interference and computational expense by focusing on real-time data processing. IL-ASGN demonstrates its effectiveness in tackling high-dimensional, non-linear, and time-varying challenges. For instance, in neuroscience, it captures the neuromodulatory impacts on sensory systems, whilst in robotics, it supports adaptive decision-making for dynamic environments. Thus, the translational potential of IL-ASGN spans disciplines. I'll briefly introduce some examples here. Sensory neurons adapt to repeated tactile stimuli, revealing principles of predictive coding in neural circuits. IL-ASGN models these dynamics by simulating prediction errors through the executor and refining the guide's causal inferences. This facilitates biologically plausible simulations of sensory adaptation and novelty detection. Causal modeling of neural dynamics. The guide uses Bayesian inference and structure learning to model causal pathways such as arousal leading to retinal ganglion cell neuromodulation. The executor simulates retinal ganglion cell activity using biologically plausible mechanisms like spiking neural networks. Synaptic plasticity mechanisms. Synaptic plasticity emphasizes mechanisms such as spike timing dependent plasticity, STDP, and its role in sensory processing. IL-ASGN builds on these principles by modeling causal relationships between synaptic changes and behavior in the guide and validating these hypotheses in the executor through large-scale simulations of synaptic activity and circuit dynamics. Scalable neural simulations. A key aim of IL-ASGN is development of large-scale neural simulations such as GPU-enhanced neural networks, GENN, focusing on scalability and biological plausibility. IL-ASGN incorporates these principles by using the guide to manage high-dimensional causal modeling on GPUs, whilst employing the executor to simulate spiking activity on neuromorphic hardware. This hybrid framework should greatly economize on processing, stabilizing it at scale. Robotics and real-time decision-making. In robotics and real-time decision-making, a similar hybrid framework facilitates advanced navigation and decision-making, blending biological plausibility with computational power. Here, however, the guide is suited to running on neuromorphic hardware, whilst the executor is on conventional GPUs. In this scheme, the guide pre-processes sensory inputs, such as edge detection and motion analysis, using spiking neurons and local learning rules, and simulates biologically plausible sensory adaptation. The executor, on the other hand, handles reinforcement learning, trajectory optimization, and counterfactual simulations. Thus, the executor complements the guide's sensory pre-processing with high-level reasoning and decision-making based on an AN. For example, a robot navigating a cluttered environment could use the guide to pre-process visual inputs rapidly, whilst the executor generates navigation strategies based on reinforcement learning. Using this method, we may also investigate predictive coding phenomena and how these impact anomaly detection in real-time decision-making processes. In conclusion, IL-ASGN offers a groundbreaking framework that integrates inferential learning-derived synthetic gradients with causal inference, offering significant advancements in efficiency, scalability, and causal inference, and causal understanding for large-scale AI applications. By leveraging hybrid hardware, IL-ASGN extends its potential for real-world deployment, combining computational efficiency with practical applicability. This framework streamlines backpropagation, enhances parallelizability, and embeds causal reasoning into the learning process, addressing critical challenges in deep learning. It represents a major step forward in aligning artificial intelligence with the biological principles that inspire it, creating a system that is both computationally powerful and deeply interpretable. By bridging the gap between scalability and interpretability, IL-ASGN not only resolves current limitations, but also unlocks new possibilities for interdisciplinary innovation. Its potential spans diverse domains, architectures, and data environments, making it a truly transformative approach to AI design. So during my PhD journey, my goal is to develop and validate the IL-ASGN framework, a scalable, efficient, and biologically plausible neural network model. The timeline is structured into 3 phases, each building upon the previous to ensure steady progress from foundational work to advanced applications and dissemination. Foundations. In the first year, I will focus on laying the groundwork for IL-ASGN. This includes developing a baseline implementation and validating it on toy datasets. Key tasks include designing and implementing the guide and executor networks to decouple learning processes, benchmarking experiments to evaluate parameter interference, synthetic gradients, and computational accuracy, exploring initial applications in neuroscience, such as basic models of neuromodulation, and this phase will help establish the foundational components and test their feasibility in controlled environments. So expansion, in the second year, the focus shifts towards the scaling and expanding IL-ASGN. Here, I will validate the framework on larger, more complex data sets and expand its applications to neuroscience, introduce structure learning to isolate causal pathways for applications like robotic sensory adaptation and decision-making systems, optimize IL-ASGN for hybrid hardware part platforms such as GPUs for the guide and neuromorphic hardware for the executor. And this phase will demonstrate IL-ASGN's versatility, scalability, and real-world applicability. The final year is dedicated to advanced applications and dissemination. This includes testing IL-ASGN in robotics and real-time adaptive systems, such as anomaly detection and predictive coding, conducting comprehensive evaluations of the framework's performance in both synthetic and biological models, writing my thesis and disseminating findings through academic publications and conferences. By the end of this phase, IL-ASGN will be a robust tool ready for interdisciplinary applications and future research. Ultimately, this timeline reflects a structured, milestone-driven approach to achieving the goals of my PhD. It aligns foundational research with progressive validation and application, ensuring that IL-ASGN contributes meaningfully to the fields of neuroscience and artificial intelligence. So I'd like to thank Bayesian for making me aware of synthetic gradient research, and my prospective supervisor, Chris Buckley, for his oversight in the preparation of his work. And yeah, so thank you for your time and attention, and I look forward to your questions.
Thank you, Mark, for the wonderful presentation. So any of you that wants to open their camera and give Mark a round of applause and maybe unmute yourselves. Thank you for this wonderful introduction to what you want to do for your PhD. So now we'll be opening the floor to questions from the audience. Let's see if anyone has any question, and if not, maybe I'll just ask a very low-level question, whether you have had the opportunity to test the network, test the model in any way, whether you've played with some, even just smallest of toys of examples to see how it works.
I haven't got any direct experience with sort of prototyping this network, but I've got a lot of background in sort of more conventional sort of machine learning. So as I mentioned, it's quite similar to a GAN in a way, with the generation of the synthetic gradients, and it's got that sort of that mixture of Bayesian and sort of frequentist approaches that is sort of seen in I don't know, a variational autoencoder or something like that. It's and I've got a bit of experience with DCM too, going back to the old my old sort of time when I was looking at neuroimaging data. So I think in terms of doing preliminary work, I haven't directly engaged with trying to start prototyping, but I've got a like decent background, so I should be in good stead when I start trying to do so. I mean, I basically took a long look at Baron Millige's excellent code from the paper on how predictive coding approximates backpropagation in arbitrary computation graphs, that paper, and he had an excellent sort of GitHub associated with that. So I had a good look at how to sort of code inferential learning, and I've practiced a lot with looking at backpropagation and inferential learning and predictive coding through that sort of thing.
All right. And okay, so if I may ask a further question before opening the floor even more. I know you are just now proposing a PhD thesis, so you are probably envisioning the goals of the thesis at a sort of higher level, and I saw the ones that you listed. Do you think of any specific problem that you would want to apply, ideally, this architecture that you're proposing? Is there something that ignites the passion inside you that you want to follow?
Yes, there is, and I think it's not one of the it's not so much these sort of neurobiological applications, but it's just being able to sort of more efficiently train a sort of vanilla network that could be doing anything, like a neural network as opposed to a neuronal network, although it could do both. Like it just when it can look at if we can look at sort of modeling, how to model problems that might come up in industry and commerce, and sort of make these networks just flow a bit quicker and achieve the global minima in a faster time through a more robust sort of Bayesian framework that's guiding it down. That's what sort of interests me primarily about it. So I envisage that if my sort of overarching goal would be to produce a sort of toolbox that allows you to sort of sync your own network into mine, and allow that to expedite training of it. So in a modular approach, sort of plug and play, how can I speed this up? How can I reduce? Because of course, we know that the data consumption of neural networks is getting to be a big problem, and everyone wants to save time and save and sort of save time in sort of training. Yeah, so that would be my sort of thing I'm interested in.
Thank you for the answer. Okay, so any other question from our audience? Let's see. Okay.
Hi.
Oh,
the camera on.
hi, Chris.
Hi. Yeah, thanks for the presentation, Mark. Just as you go forward with this, I think I mean it's a very ambitious architecture you've got there, but the way you present it, it feels like a finished architecture somewhat, and you might want to you know, present it and then and be very clear that this is something that you want to move towards rather than a finished architecture. I think that can, you know, perhaps yeah, a bit off-putting to some people. You have to start with some basic ideas and bring to them, and then point at the future of this architecture that you'd like to design, just as a style thing as you you know, go for PhD proposal interviews and so on. And obviously there's lots of very nice ideas in here. I guess at this point, until you've actually started to construct this, I mean, so from what you presented there, it's very hard for me to understand the details of what this thing would actually achieve. So I'll ask you some questions about that in a minute. And I guess if you've not played with this, I mean, you seem very confident about the synthesis of all these ideas. I guess, I mean, how confident are you that it's going to work? Because often the proof is in the pudding with these things, right? You have an idea and then it all falls down at the coding and so on.
I think it doesn't do anything particularly out of ordinary that hasn't been shown. Like I take the point that I've sort of presented it in a slightly curious way, that it sounds like I might have done it, and I need to avoid doing that. So maybe the best thing to do would be do a bit of preliminary work and then sort of make concrete what's been done and what hasn't been done. But the sort of ingredients for this thing are all existing. So the work on synthetic gradients is there, and that's a basic sort of like a generative adversarial model. That's a basic thing that sort of exists. And the work for inferential learning is there. And really all it is doing is using inferential learning in one network, using an inferential learning network to fit gradients to a back-propagated network. That's where I start with this.
So when you talk about synthetic gradients, you talk about the Joseph Mourinho work. Is that right?
I can't remember the paper now, but it's decoupled neural interfaces.
Okay, it's not.
Was the paper.
Okay, we can sort that out later. So one of the core tenets of this is that you're going to solve some of the computational expense of backpropagation. But one of the problems with inferential learning, obviously, it's very expensive, right? Because the inference phase adds a lot to the computation over and above the backward pass within a normal neural network. So I assume that you're thinking somehow this synthetic gradient thing is going to sort this out, but I'm not quite clear how.
Well, with predictive coding, you're running to the equilibrium, but with inferential learning, there are genuinely positives to it that sort of counteract that you have to iterate so many times. With each step in iteration, it does tend to step more accurately in the right direction. So I wasn't thinking that we'd run to equilibrium to predictive coding. I thought we'd run inferential learning, which is sort of predictive coding sub equilibrium, as I understood. So I was thinking that in terms of the advantage.
So in inferential learning, they don't do many steps of the inference, but still they're still more computationally expensive than backpropagation as they stand, and also they lack the accuracy and haven't been shown to be able to train in large networks. And on the positive side, I think there's been lots of rhetoric about what doing inference does over and above backpropagation, but that's still ongoing work. Something we do in our lab is to show that concretely, because I don't think that's ever been shown other than pointed to, and have some intuitions about why it'd be good, but actually there isn't any really concrete demonstrations as it stands about that. But it's just about this computational expense. So inferential learning is more computationally expensive, because instead of this kind of one backward sweep, you have to do at least as many inferential steps as the size of your network, actually 2n, so you can get the information up and down, right? So it's always going to be computationally more expensive. So Do you see somehow that this synthetic gradients is going to cheapen that expense or somehow nuance that? I don't know.
Yeah, sorry, I see that like combining it with back propagation and through synthetic gradients will cheapen that expense. I should expect, because it's just correcting by going in and correcting for interference, particularly that sort of a horrible associative form of interference, and sort of making adjustments that are more Hebbian. I think it might actually just compensate. It might stand a chance of actually just proving to be the more economical approach. But I haven't shown that yet, and you're absolutely right. But I was kind of thinking if we could just run even a few steps and sort of.
So can I just say, so you intend to do backprop and then inferential learning, is that right?
No, the inferential learning would be used to guide a second network running backprop. That's so you're using inferential learning to predict synthetic gradients for a network running backprop. And the back-propagated network is creating its own gradients through backprop, but the synthetic gradient network, the inferential learning network is predicting synthetic gradients. So you're using inferential network to predict synthetic gradients. You're running a back-propagated network to produce the true gradients, and you're computing a cost function, or using that to perform a cost function.
So in that description, it's definitely going to be more computationally expensive, right? So because you did say at the beginning that you wanted to ameliorate the computational cost of BP, but that already sounds much more expensive, right? So you'd have to have some proper functional benefit to do that, right? This interference thing that you suggest.
Yeah, it's just guiding as it descends. It could almost be run in phases, and I think that's kind of the key to it. That you just don't want the network as it trains to get stuck in a local minima. You don't want it to sort of behave maladaptively and for interference to build up. So even if you can apply, not all the way through, but not consistently, but inferential learning in phases to correct through synthetic gradients, just to nudge it in the right direction at the right time. And I think that might be sufficient to enable sort of an economical application there.
At this stage, it's a hypothesis. We don't know whether that's true. Also, we don't have problems with local minima and in backpropagation in large neural networks with stochastic gradient descent. Right, there is no local minima. What we have is valleys and low gradients. Right, that's the kind of vision you have of neural networks these days, not local minimal. Right.
Sure. It's analogous almost to a hyperparameter search, though, and it's like you're using a Bayesian framework as you often would with in TensorFlow, where you set your Bayesian hyperparameter search. That's kind of what inspired this in some ways. I thought that this is another way of doing it. It's allowing a Bayesian complement that has some complementary knowledge to the backpropagated version
Yeah. So when you say uncertainty, you mean over the weights of the parameters? You mean uncertainty over the parameters or the states?
Uncertainty. So quantifying. Yeah, quantifying sort of uncertainty over the weights. Yes.
Because predictive coding doesn't do that out of the box, right? We have point estimates on the weights in the standard optimizations, and you have to do a lot more legwork and a lot more computation actually to get any kind of distribution over the weights. It's not in the literature as it stands, right? People typically do point estimates on the weights, right?
Oh, so do I mean in uncertainty over parameters then?
But yeah, weights are. I'm considering weights as parameters here, right? Yeah.
Sure, but yes, of course. Sorry.
So predictive coding is kind of very mildly Bayesian. I think Carl wants us to call it MLPC because there's lots of approximations on top of those foundations in variational inference, which are point estimates. So that actually the uncertainty bounds and the Bayesianness of it is somewhat in the ML scaled up versions is not particularly strong. So you'd have to do you'd have to put proper distributions over weights, proper distributions over states. So you have to keep track of second order statistics, which is not actually done in the inferential learning literature as it stands, right? It's all point estimates at the moment. So I was wondering if you have how you would do that. What's your?
So sorry, could you just repeat that again? Sorry, just the last bit.
Yeah, so it's just PC has got its foundations of variational inference, but we do take point approximations everywhere when we try to roll these up to large machine learning systems. So you don't get any sophisticated distributions or posteriors, right? You just get a point posterior, essentially a map, right? And so you don't have you seem to want to take use this Bayesianness somehow in your architecture, but it doesn't come from PC itself or inferential learning. You have to put some extra functionality in there, and that's an outstanding question, how to do that well and computationally efficiently, right?
Sure, I could sort of see the context, modeling counterfactual, modeling sort of counterfactual sort of propositions in the context produced by the inferential learning network, because you could certainly do that. You could certainly sort of take a bit and use and clamp it differently and sort of operate on in that way using a structure learning approach.
So yeah, can you unpack that a bit? I don't quite. What are you clamping?
There are sort of, well, I mean, I mean, sort of simulating. I guess it's slightly different to uncertainty, but using the structure learning capability to sort of say, is this bit directly modulating here or here, say in a neurobiological interface? You'd sort of be saying, you know, is the amygdala modulating the RGC, and or is it coming from this other thing? So you can address these sort of causality questions, and there surely be an uncertainty associated with the parameters there, with the weights there.
Okay, I'm not entirely clear on how you do that, but I guess, yes, so there is some work on causal reasoning in PC, so there's Tommaso Salvatore's work that you perhaps...
Yeah, I mean, you could certainly do that with inferential learning too. I would think you could sort of you could address sort of counterfactual stuff, or
so just to drill down on what you mean by counterfactual. So there's usually you mean by counterfactual, you're keeping some kind of sophisticated posterior over many types of outcomes in your system, right? But in things like PC, we're keeping a unimodal posterior, so we don't really have counterfactuals, right? But I'm guessing is how are you going to get counterfactuals out of these systems?
I must have misunderstood counterfactuals. I'm sorry to say. I think what I really meant just merely was like if it wasn't operating like this, but it was operating like that, what would the AIC and BIC be under those conditions? Sort of comparing across metrics like that. Sort of. I mean, I just there surely is just still scope for structure learning or causality modeling within inferential learning, and therefore I'd say if you're using an inferential learning network to predict synthetic gradients for a back-propagated network or another network, then you can.
I agree. I know you're alluding to the Bayesian roots of this. I can see that. So I mean, just to submit, I think when you do present this, if you get to the interviews in your PhDs, I think you need to start from a much more. You're not expected to have a fully fledged architecture at this point, right? And so you can make clear your intuitions and what you have done and what you haven't done and what you'd like to do, where the intuition comes from and what you test. I think you'll get yourself into trouble if you make out that it's a finished architecture and you haven't run it, right? So I think just think of the way but I mean, there's a lot of ambition here, Mark. You've obviously thought about all kind of wide-ranging selection literature. I'd probably advise you to pare down what you present a little bit, because you're including so many things in this, right? I mean, it's a really grand vision of layered different ideas, but there are pieces, all these pieces that you want to do are themselves challenges, right? And some of them are PhDs within themselves. So, you set out a very ambitious program for a PhD. If you got that completed and competing with backprop, I mean, that would be an amazing thing. But you don't have to do that to get a PhD. Each one of these pieces of questions that we've talked about there could be a PhD in itself. But yeah, that was very interesting. I think I'll let Carl give you some feedback. Thanks, Matt.
So if there are no other questions from the audience, thank you so much, Chris, for your input. I think it's Carl turns right now, if I'm not mistaken.
Is it my turn now?
Yeah, it seems so, Carl.
Excellent. Yeah, well, all the hard work's been done by the presenter and Chris. That's quite good. You may not need me on this one, but I will give some feedback, and perhaps if Chris is available, just ask for some clarification about some of the fundaments. Mark, that was a very clear presentation. You did read it. I suspect that sorry, let me back up. The situation then is that you have been, or you are considering competing for a PhD under Chris. Is that right?
Yes, correct, Carl. Thank you.
And you have to do a presentation, I would imagine, to get onto the rotational scheme. I don't know this, but I imagine that's the case. I'll give my feedback at two levels. Really, maximizing the chances of you being accepted onto the scheme, and very much along the lines that Chris was intimating. And then a second level of feedback that will be more useful in terms of if you were successful, or if you wanted to refine the proposal in terms of the the underlying ideas and ambitions. So the first thing is it was extremely clear. It's the clearest that I've heard you talk about these things, but you have to rehearse it so it doesn't sound as though you're reading it. So
Sure.
it has to sound, so it's all in your head. And it just comes naturally. So that's the first thing. The second thing is just to reiterate the very important points that Chris has made. At the moment, you almost sold this as if you were pitching to a company, or you were sort of trying to sell an idea, talking about breakthroughs, revolutionizing this and that, and overselling the potential. So you want to become a humble junior scientist and be much more circumspect about the potential, and in so doing, emphasize not the novelty of all the component pieces. As you nicely articulate, a lot of the component pieces are out there in the literature, and they have an established validity. But emphasize the novel composition of established bits of work. So instead of just mentioning something like synthetic gradients, have a reference on your PowerPoints, possibly with a diagram. For example, I noticed well, let me ask you, the nice diagram with the conventional backprop and local PC message passing, did that come from Baron Millage or Chris's work, or where did you get that arc?
That was it was from someone called MJ DeBerg, 2016.
Okay.
That he's taken it from our paper. That I recognise that figure. That's Barron's figure, the one on the PC.
Brilliant. Right. Yeah. So if you can do that for every word or concept you introduce, that will be much more compelling. So what I'm saying is, if you can ground your proposal in terms of state of the art that has been published within, in the recent past, with a graphic or with a reference, and then highlight the novelty of what you would like to do in terms of the way you're putting these things together, I think that will be much more compelling for a selection panel, as opposed to I repeat, as opposed to you doing a pitch, trying to encourage people, invest in this kind of thinking, you make millions. That's not going to work for a PhD selection. They want to know what's the depth of your knowledge and the confidence that you have in that knowledge in relation to what has been achieved so far, and how are you going to take the field forward from that foundation. And I can't resist just appealing to Richard Feynman's second note, beyond that which I cannot create, I do not understand, which was know how to solve every problem that has been solved. So you need to be able to convince the panel that you know the literature, and one way of simply doing that without wasting time memorizing it is just by having those kinds of graphics that you used from one of Chris's papers, just to substantiate the fact that this is established technology. And what you're doing is joining the dots. You're putting them together in a potentially new way. And then instead of saying it will revolutionize, if this is successful, it will provide a revolutionary approach to, or a new approach to the extant problems with conventional backprop and machine learning. So I think that was wise advice, which is, just the way that you frame this presentation. You're not trying to sell the idea; you're trying to sell yourself. And there are ways of doing that. Is that useful?
That's incredibly useful. Thank you. Yeah, it's so I think what I did was I wrote a research proposal, and I thought I was quite pleased with the research proposal, but then I just sort of made it into a presentation, which wasn't, I knew sort of on some level wasn't the correct way of doing it, because as you say, just sort of reading it off, it didn't make sense to port the research proposal into the presentation in that sort of way. But certainly I think, as you're saying, the sort of Feynman quotes and that sort of stuff, if I just ground it with what exists already and don't oversell it, then I think I stand a chance of presenting it more confidently if I'm actually invited to interview.
Sure. And what will make you more confident also is just to at least half, if not more, the content that you want to cover. Because if you go in there and you've got 20 minutes and possibly even 10 minutes to tell your story, you're going to be very anxious that you're not going to have enough time to get everything in, and you'll feel rushed and you'll feel you haven't done due service. So just pick out the big themes, and they can either be the early themes at the beginning of the say certainly of your sort of roadmap for the PhD, or the things that you need to solve first before you move on. So I'll give you a simple example. At a very broad level of analysis, you could be devising a scheme for doing things that neural networks do, which is, say, like generative AI, generating some content. Or you could be devising a scheme that generates executive commands or predictions of the kind you'd find in robotics. Or you could then move on to a third level, which is to do planning and counterfactual reasoning, and approach true understanding. So these are three distinct sort of aims or functionalities, and I think you should focus on just one of them, and then mention that you can, if you follow this advice, then if you focus first of all on the foundational architecture of this combination of synthetic gradients, GAN-like architectures, and variational Bayes, or predictive coding, then you can say, if we can do this, this now affords the opportunity to actually take it into an active aspect, active predictive coding, or and associated approaches of the kind that will be useful in robotics and autonomous vehicles. If we can do that, then we can go to the third phase, which is to actually do counterfactual reasoning and future pointing, and using it as a simulation engine in order to evaluate possible futures under different policies, and that will be active inference. So I'm making a distinction in predictive coding, where everything is a reflex. It's just control theory made Bayesian. Well, no, you can go in further back. So predictive coding, its original flavor, was just an efficient way of representing things. So predictive coding was introduced to compress sound files in the 1950s. So it's all about data assimilation, and it's just about the efficiency of representing things, a little bit like, say, current transformer architectures and large language models. Then you move on to predictive coding in the setting of actually controlling things. This is manifested in terms of things like linear quadratic control, and then all the augmentations of that, that could be cast in terms of KL control in engineering and robotics. After that, you move into active inference, which is beyond KL control, and it's actually evaluating counterfactual futures under a well-defined set of policies, which I think is what you were trying to describe in terms of these counterfactuals. And I imagine that you were trying to answer Chris's question about, well, where's your measurement of uncertainty that is necessary to propagate uncertainty into the future? And I think your answer was, well, I can look at the uncertainty from the point of view of building counterfactual futures under different model structures, and I can use the BIC or the AIC or the free energy as a measure of the goodness of this structure or the future under this structure. However, I think all of these issues would burden the presentation far too much. So you just mention these things so that you don't get the awkward question from Chris, well, how on earth are you going to measure the quality of a particular policy if you don't have a measure of the uncertainty over either the parameters or the latent states or causes? So if you just stick to the foundational, the sort of predictive coding first, sort that out, and then just tell your audience, if I can solve this, this opens the door to active predictive coding and an efficient way to learn to control, learn to plan, learn control as inference. And then if that's successful, then I can, in the long-term future, move on to active inference proper, which is learning to infer to plan, if you want to amortize everything. But control as inference and planning as inference are very different things. Control as inference is just having a clever thermostat that is context sensitive and does all the right things. Planning and counterfactual futures are very distinct. That does require you to roll out into the deep future with a time horizon, with uncertainty as part of the mechanics in order to avoid heuristics like temporal discounting, for example. So in active inference, what stops you looking too far into the future is the uncertainty that accrues, but you have to actually explicitly estimate and quantify the accruement of uncertainty as part of the planning procedure. So if you focus on the first part, what are the big ideas here? And it struck me that the big ideas seem to be, first of all, synthetic gradients, a mixture of synthetic and true gradients, a commitment to predictive coding and local optimization, and crucially, amortization of a particular sort where you're using one network to predict the synthetic gradients for another network. Have I missed anything in terms of the big, the architectural pillars of the foundation of these kinds of networks?
No, I think perhaps with amortization as well, it was just a very simple thing of amortizing by caching and reusing the sort of the synthetic gradients themselves, so that you could always be sort of ahead of back propagation, so the network wouldn't be held up as much. So that's also what I meant by amortization. But I think you've hit all the key sort of ingredients to it. Yes.
Right. Yeah. I mean, I was reading the amortization bit as the deployment of a GAN-like architecture, or your sort of networks A and B that were slowly able to predict the requisite gradients. One network predicting the requisite gradients for the other network. Yes.
Better.
Now, and this may be more a question for Chris, but let's see if you can answer it. What is first of all, you talked a lot about synthetic gradients. These are presumably gradients of variational free energy with respect to what? To the parameters or the states?
So a synthetic gradient. So the synthetic gradient would be created through. It will be predicted. Well, it's predicted, and it's a gradient that replaces the back-propagated gradient. It's just as simple as that. So you've got it's generated through an inferential learning process, which is the Cauchy descent of free energy. but it is a gradient that's output by that network, that's actually predicted by that network as the output variable, and it's an equivalent or a sort of an isomer for the sort of gradients used in back propagation. So that's all it would be between two.
I see. Right. Well, so this may be something that Chris can answer. Does that mean you're reifying backprop gradients via the chain rule as the true gradients?
I think I'll let Mark, because I'm less clear about how this synthetic gradient part would work. So maybe Mark can answer.
Sure, yeah, you'd be reifying them by combining them by creating a loss between the synthetic gradient and the actual observed gradient between those two nodes. And you'd use that node to sort of reify the ability of one network to predict synthetic gradients and the ability of the other network to do whatever it's doing, but in response to receiving the synthetic. So it would sort of just corrects course a bit.
Right. I think I'm asking a sort of slightly simpler and more challenging question. When you talk about the true gradient, do you mean the gradients you get from the chain rule in backpropagation schemes?
Yes.
So these are gradients on the weights. The gradient, the rate of change of the objective function with respect to the weight or the parameter of the model.
Yes, these are the gradients of the back propagated with respect to the parameters using the chain rule.
Right, I see. Yeah. Okay, so this may or may not be useful, but I would not regard those as the true gradients. They're an artifact of back propagation. The true gradients are simply the local gradients of time averaged gradients at that node. So if I am right in that, then your agenda could be easily critiqued because you're chasing true gradients or trying to emulate true gradients where the true gradients are not fit for purpose. That's the whole problem with backprop. They are not the gradients of a given parameter with respect to the objective function, which in this instance would be an elbow or a variational free energy.
That makes sense, but wouldn't it be just quite trivial to compute the actual sort of true gradients and do it with them as well, or do it with them instead?
That's why I'm asking the question. So I've always had a problem with certain applications of amortization in that you don't need to amortize because they are locally and directly available. However, the gradients with respect to the parameters are not instantaneously available. So they're not local in time. So you have to take a time average of the local gradients with respect to the parameters. Now, the gradients with respect to the states are explicitly available, and there's no point in amortizing that because they are time varying and easily computed locally. That's the whole point of a predictive coding architecture. But the gradients that you need for the weights are not quite that simple, because what you need is an estimate of the average gradient over all the data that you are going to try and assimilate or learn. And of course, you don't have access to that online. So what do? Well, you have to take basically a trace or a path integral of the gradients to get the gradients that you to get the gradients for the parameters, and that introduces an interesting distinction between why I'm saying that is that's what your idea of mixing synthetic and true gradients in a way that affords a certain degree of adaptability could also be read as treating the gradients with respect to weights, which are local quantities. So forget about backpropagation. This is, that's not the way to do it. This is a local thing. you could treat the true ones as what you would see if you did an infinite path integral over all data that you will ever see and you have ever seen. And the synthetic one as a very noisy version of it, or perhaps the other way around. Let's stick with this, but you might want to switch it around. But you've also got instantaneous estimates for this particular frame of a video, for example, or this particular content, that you can now think, well, perhaps it's the case that the parameters do actually adapt in the spirit of, say, continual learning. But the question now is, how quickly do they adapt? And one way of parameterizing that is to take the history of the gradients and use that to update the parameters and change their adaptability by changing the length of time over which you're integrating the gradients. And one simple way of doing that in the spirit of the TD algorithm, and indeed, simpler versions of that, like Scalar-Wagner or just trace operators, where I'm using trace in a particular way, is just to adjust with your lambda the contribution of the instantaneous gradient with respect to the weights to the time averaged or the accumulated, which we could call the true. Let's go to the to the true gradient. So now your gradients will now fluctuate a little bit with every new data point. If you don't want them, if you want them to fluctuate in a very small, with small fluctuations, and remember the deep past, as you would if your environment was non-volatile and constant, then the contribution of each new gradient would be very small in relation, lambda will be very small in relation to 1 minus lambda, which is the accumulator of the gradients. So that will be one way of incorporating the TD aspect, but applied now not to reward prediction errors, but now applied to prediction errors of a particular sort. If you now, and this is quite crucial, if you now read prediction error as a euphemism for an elbow gradient or a variation free energy gradient, which of course it is in a straightforward way in predictive coding because of the Gaussian assumptions about the states and possibly the parameters, but you can generalize that notion and just use prediction error as a euphemism or a synonym for the gradient that defines your coordinate or your gradient descent. And if you so tell a story and then show references to temporal difference models in dynamic programming, you can say now what basically, if we just read now this as in the context of reward prediction errors, themselves provide a kind of gradient, and apply that notion to the gradients we want to optimize, which are the local gradients with respect to the parameters of the weights of the generative model. What we can now do is use that kind of TD lambda scheme to tune the adaptability or the plasticity of the learning. So in very volatile environments where the parameters have to change very quickly because things are changing, contingencies are changing, the weather is changing, the stock markets are changing, you would actually have quite a high lambda, and you would be, if you like, looking less into the past. You'd lose the memory of the gradients. Whereas if you're in a very non-volatile environment and you wanted to imbue or assimilate all the information into the deep past, then you'd have a very small lambda. So that might be one way of selling that that gets away from the notion that the true gradient is a backprop gradient. It's not. The true gradient is simply the gradient of this parameter or this latent state or this latent cause with respect to the elbow or the variation free energy, full stop. You don't need to talk about machine learning or backpropagation of errors to know that. The question is now, how do you estimate that gradient, or how do you do that? And then you can move into, well, one graceful way of doing that is to look at the problem of parameter learning or machine learning as estimating a path integral of the gradient based upon observations, and then you can use your TD alpha, your TD lambda approach. I'm just trying to think how you'd whether amortization, whether your generative your GAN thing is necessary in that sense. I think you could certainly sell it like that, in the sense that you can learn the gradients. Then you can your synthetic gradient now becomes the accumulator, and then the true instantaneous gradient can be added to that to a greater or lesser extent, to give you now a universe of different models that will cope with different volatility environments. There's a reason I'm pursuing that, because that has a very close connection with generalized filtering, where you're now changing you're treating the weights as very slowly changing states. And if you can do that, then you can solve the problem that Chris was confronting you with, which is representing the uncertainty of the weights. Because if you're treating the weights as states, and you've already got a predictive coding scheme that represents the uncertainty over the states, you now also have the uncertainty over the parameters. And now you don't have to use a BIC or an AIC. You can now actually use the free energy. And I slipped that in because I did notice you referred to the AIC and the BIC. These are appalling estimators of the elbow. They will fail. They're fine for reporting p-values in your sort of +1 paper, but when you actually come to use them in order to do model selection or gradient descents, they fail abysmally. And that's because they only use a law of large number approximation to the complexity. But the complexity is itself a function of your posterior and your prior. And those have to be full with no functional form, full distributions. So that's why Chris was saying, you can't measure the complexity or the evidence or the AIC. Well, in fact, you can actually with point estimates. That's the whole point of the AIC, the BIC. But that's why they don't work. That's why you have to have the full posterior over the thing that you're trying to optimize in order to so that you can evaluate the elbow or the variation free energy and its gradients. If you don't have that, then you recourse to the IC. So I'm just putting a little bit of technical detail in there. Do not, if you think anybody knows their game, do not use refer to the BIC or the AIC. They're fine for sort of reporting scientific empirical results, but they're not an appropriate thing to provide gradients for coordinate or gradient descents. So that's your TD alpha and your GAN playing the role of accumulating the evidence. What was the third pillar? Can you remind me?
So we had synthetic gradients, we had the TD alpha, we had variational Bayes, and we had inferential learning.
Right. Okay. So yeah. So can you just and again, if Chris has a more concise answer, what's the definition of inferential learning?
So I was just assuming that inferential learning was predictive coding, using the predictive coding framework, but not running to equilibrium.
Yeah, so it's just been used as recently as a kind of a group label for lots of local updating schemes. So I think people can't cast equilibrium prop as an inferential learning algorithm. It was just a kind of broad label for a set of kind of local updating schemes. Inferential learning came from this relation to inference and predictive coding, but it's used as that kind of broad label, right? And yeah, I think Mark is right there. So it's inference sort of, so they don't do proper gradient descent to the equilibrium. They just do a few steps, and there's all these little papers on when you should do inference steps at what layer and so on. So it refers to a set of algorithms that sit upon this kind of local updating schemes, essentially.
I see. So this comes back to this notion that you do some kind of abbreviated or truncated inference before you update your weights, and then you schedule it in the work.
It was coined to distinguish backpropagation from other schemes that are not backpropagation, essentially, right?
Okay.
And it's got this broad sense in which you can play around with things within it. So it's not variational inference in its pure sense, right?
Well, I mean, if it's doing a gradient, if it's just doing a few iterations of a coordinate descent, and there is variational inference, it's just early stopping, I would imagine. Which I assume is what Mark meant by not getting to the equilibrium. I see. Okay. And what was the alternative, Mark? It was inferential learning versus. Sorry, it's backprop, isn't it? Right.
Yes, it was backprop. Yeah.
Yeah. Right. Which, yes, I see. No, yes, do I see? Sure, I do. Okay. Right. So, yeah, this is more really for your panelists or potential supervisors. But the discussions around inferential learning will seem quite strange to those people doing KL control and using predictive coding in an active context.
So
indeed,
it was coined in for kind of static machine learning problems. I think that's another comment.
Yeah.
Mark, you run the gamut of applications into robotics, into machine learning. I think you should pick one particular application and then do it as concrete as possible in that. But inferential learning was coined in terms of classification of images or generation of images, but static problems with no dynamics.
Okay, that's really useful. So yeah, just to pick up on that, Mark, I think you need to identify what kind of scheme or algorithm you are wanting to create. So there's a very bright line between solving static problems with no dynamics and problems of data assimilation in the context of state space models and control theory and planning. So there is no inferential learning in the more general setting of assimilating time series or control theory, because you are doing your gradient descent to optimize your posteriors over the states and the parameters online continually. So there's no scheduling issue. And the way that is done is by generalizing your latent states from just the current value to their motion, to their dynamics. So the simplest example of this is a first order linear Bayesian filter, which is called a Kalman filter. So a Kalman filter has under the hood both x and x dot or dx dt. And as soon as you do that, you're in the world of generalized coordinates of motion. And that means that you can effectively model the future. So what you do is you instead of chasing the equilibrium, when you're working in generalized coordinates of motion, your equilibrium, well, what can happen if you don't have generalized coordinates of motion, you just deal with the static problem of there is a latent state causing this content on this data, is that you have to go to the equilibrium and then ideally, and then do your parameter update, or indeed your update about the latent state. But that's in a dynamic context, that equilibrium is always moving. So you're always chasing a moving target. And one way to solve that problem, or heuristically the solution that things like Kalman filtering and Bayesian filtering uses, is to actually make the problem into a problem where the target is rendered stationary in a moving frame of reference. So instead of chasing a moving target, what you do is you chase the target in a frame of reference that moves with the target. So you can get to your equilibrium as time moves forward. But to do that, you have to estimate the moving frame of reference, which means you need a latent cause, that is the velocity. And you can generalize that notion because the velocity, the equilibrium in the joint space of x and x dot is itself moving. So you can go to x double dot and x triple dot, and usually you need to go to about 3 or 4 for nonlinear systems to do that. So if you wanted to, you could say, I'm first of all going to demonstrate this this idea with the 2 pillars in play in the context of static schemes, where there are issues like inferential learning. If that is successful, I'm then going to generalize it into generalized coordinates of motion, which will enable me now to resolve the inferential learning problem and apply the scheme online in a way that then ultimately can be extended to do control theoretic or applied to control theoretic situations. So, the meme here is that your Bayesian filter, and it can't be a smooth, it has to be a filter because you're doing this online in a real world application. When equipped with a control variable, becomes linear quadratic. A Kalman filter becomes linear quadratic control. They are the same thing, basically. And then that basically means that you can generalize that hierarchically in terms of nonlinearities into an extended Kalman-Bucy filter, and then that becomes more generically KL control. And that's state of the art in terms of robotics control. And that's, I think, where you would ultimately be aiming. But I think you have to decide and understand the distinction between predictive coding for static machine learning problems and predictive coding for state space modeling, data assimilation, and control theoretic applications, because the solutions for one set of problems go away. The problems that are being solved in the static context just aren't there in the dynamic context, simply because you're a more expressive generative model. So, do you understand that? Is that something you've come across before?
I've certainly come across Kalman filters and Kalman-Bucy, and I do think I understand what you're saying is that for a static problem, we could use inferential learning for static machine learning data, but if it's a more dynamical system, such as adaptive, then what we'd need to do is use that sort of like a Kalman filter to predict the synthetic gradient, something with a moving approximation of the equilibrium.
Yes,
but
right.
I think, yeah, but we could still use in each of those inferential learning, and the Kalman filter is Bayesian, and in that context we can still do structure learning and uncertainty, because we'd have, if we're using the true gradients, as in the gradients that are observed not back propagated but actually observed, we'd have uncertainties over those parameters. So we could use either a Kalman filter scheme or an inferential learning scheme, depending on whether we have dynamical in the Kalman filter or static in the inferential learning in the context. We can still use that technology.
Yeah, absolutely. Yeah, I mean, from my perspective, inferential learning sounds as if it is the limiting, simplest case of generalized Bayesian filtering or variational filtering, where you've only got one time point. And then the question is, do you wait until you get to the fixed point, the free energy minima, or do you sort of accept an abbreviated descent, early stopping, sometimes it's called, just for computational expediency. So if you can solve the inferential learning problem, that's the simplest instance or a special case of the more general problem. You get to the more general problem by moving into generalized quantum motion. So if you can frame it along those lines, you could actually focus all your presentation on the inferential learning problem, saying that if we can solve this as the limiting case of a generalized filtering problem, and ultimately a generalized controller's inference problem, then that would be the obvious next step. I'm not promising that I'll be able to do it in my PhD, but that's where I like to go. And then I repeat, beyond that, moving to planning as inference, which brings in all the next layer of complications.
Yeah, just to say, Mark, I have to leave on the hour for another meeting, but yeah. I mean, just to reiterate, I think Carl, it's great advice by Carl. I think you should need focused out in the presentation, decide on one particular application, maybe inference and learning on some kind of classification problem, be as concrete as possible in that, and then you can point to the rosy future in generalized filtering and controls inference. But yeah, keep it as concrete as possible in one particular application in the first instance, I think. Does that make sense, Carl? Yeah.
Yes, that's I've been using far more many words for many minutes. Yes.
Yeah, and definitely, I think Carl's. I think he agrees with me. Keep it as pointing towards the research rather than presented as a finished product, trying to get investment. Right. I think that will. They will on the panels, and at least in Sussex, there will all be academics. There actually be quite a wide range of academics. If you look at the PhD program, it's an interdisciplinary program. So it needs to kind of have ability to convince the people who know their stuff that you've got some understanding of the details, but also you need to broaden out and say, why are we interested in this, right? And in a broader sense, and also connections to the biology will be helpful because there'll be some neuroscientists there as well. But yeah, we'll keep it as concrete as possible. But yeah, great. I've got to run, but thanks for that, Matt. That was an interesting afternoon. Thanks for the feedback, Carl, and let's talk at another time, Matt.
Thank you so much. Thanks so much, guys. Cheers.
Cool. See you later.
Cheers.
All right. Oh, so. Oh, I think.
I think he wanted to. Oh, I have about 5 papers to show that he should read. Never mind.
Do you want me to send him an email for him to get back on the call?
No. No, I think if he just goes away with what Chris told him, that's going to be, the level at which I can help, I think, would depend upon him securing a PhD so that I can talk jointly to the supervisor and him. He's at a very early stage. I have come across him before in different contexts, but in his role at King's. So he's been sort of plugging away at this for several years now. I hope he does get a position so he can start pursuing it.
How old is he? Do you have an estimate? I had troubles situating him. Probably 25, something like that is my estimate.
Yeah, yes, I think that would be about right, actually. Yes. Yeah, he's been a research assistant with theoreticians and brain imaging scientists for, it must be about sort of 5 years now. And if he started there shortly after university, he'd be about 25, 26. Yeah.
All right. Okay. So tomorrow I'll also chair the meeting tomorrow because I asked Christoph to let me chair it as it's more up my alley. You'll see. I think it's that guy that is a journalist and spoke with you with Mike Levin, and it's an interesting talk on ontology and putting together all the Levin toolbox, the Friston toolbox, and I'm interesting to see what will come out
All
of
your
it.
favorite things.
All my favorite people, Carl. Exactly, all my favorite people. And by the way, I meant to ask you. I saw that you monthly meet with Mike. I'm supposed to also write a paper with Mike, but I haven't sent him the draft yet. Is it possible to get some recording of that? I think I'm not sure what you're talking about, whether you're talking about theoretical things or possible to attend those meetings, just to be silent and shut up and not say anything, but just listen.
Yes, I'm sure it would be. So these meetings, well, there there are ad hoc meetings where we just chat, which you would be very welcome just to sort of attend as a guest or a spectator.
Yeah.
Um, But there are other regular meetings, which I think you may be referring to. They're more specific. They're for a particular collaboration with somebody called Nick Lane at UCL,
Okay,
focusing on. So I'm not sure that it would be quite so appropriate for you to be there, because a lot of it is sort of governance in terms of specific project. However, there is a DCM, Dynamic Causal Modeling work group, to which the collaborators or the postdocs of Mike will be talking about their work, which you could also attend.
Okay.
Yeah, it's a bit more technical than the sort of the fun stuff. This is more about sort of electrophysiology and data analysis and things, but may or may not be of interest.
All right. Well, I'm trying to get up to speed on more things now that I just started at Sussex. So going into the more technical things is not something that I shy away from. I never shied away from it. It was not something that I could do immediately to secure a position somewhere to work. So I had to leverage my strengths, which were more on the theoretical abstract side. But yeah, I will just look them up on your schedule if that's
Well,
okay.
yeah. Well, in fact, in a week's time, if you can email me, I'll send you a copy to Johan so that he can put you on the email list for the DCM work group. That will include Axel, who's Mike's right-hand man at Tufts. And in addition, if there are any fun chats, I will let you know. There's non-schedule because everybody's a bit busy at the moment, but they occasionally come up, and then I'll let you know in addition to the DCM work group. Yeah.
Much appreciated, Carl. Just to be a spectator and witness my favorite intellectual heroes.
Very good.
Good, Carl. Thank you, and see you
Okay.
tomorrow. Have a
I'll
wonderful
see you
day.
tomorrow. Cheers.
Bye.
Bye-bye.